The Complementary Slackness Theorem. Using a dual pair of feasible and finite LPs, an illustration is made as to how to use the optimal solution to the primal LP to work out the optimal solution to the dual LP as per the Complementary Slackness Theorem. Firstly, I'll briefly explain the theorem, and then I will use a dual pair of LPs to demonstrate how the theorem can be used to solve the dual LP from the optimal solution of the primal LP. So if we have a normal maximization problem as our primal LP with a number of variables shown here as x1, x2 to xn, some m number of less than constraints, and m slack variables, where slack variables represent the amount of the resource that is unused when converting an inequality constraint to an equality constraint. The dual LP will be a normal minimization problem with a number of variables, shown here as y1, y2 to ym, some n number of greater than constraints, and n slack variables. The theorem states that x and y are optimal only if the product of the primal LP solution and the dual LP slack variables equals 0. And this goes the other way too. The product of the dual solution and the primal slack variables must also equal 0. Now this if-then statement has some relevant implications, but they're much easier to explain in simple English, which I'll do on the next slide. The theorem implies that if a variable in one LP is greater than 0, the corresponding constraint in the other LP is binding. If a slack variable in one LP is greater than 0, the corresponding variable in the other LP is 0. These implications also run the other way when a value is equal to 0. So if a variable in one LP equals 0, the corresponding constraint in the other LP is non-binding. And if a slack variable in one LP equals 0, the corresponding variable in the other LP is greater than 0. So using the implications of the theorem, we can use the optimal solution to one LP to find the solution to the other, and we'll be doing just that. So to help us understand this a little bit further, we're going to use this example dual pair of LPs. They're nice and simple. Primal has 3 constraints and 4 variables. Now the dual can be determined from the primal, but we're not interested in how to derive the dual, we're interested in solving it. So we've provided it here for us to see. Now to be able to perform the simplex algorithm on the primal LP, we need to add the appropriate slack variables to each constraint, so as to change the inequalities to equalities. And the LP is ready to go. So following the steps of the simplex algorithm, we look for the most negative reduced cost variable, which is x1 at -40. We perform the ratio test to determine the pivot row to be row 3. We apply elementary row operations to get coefficients of 0 in all values of x1 apart from the pivot row. x1 is now a basic variable, along with u1 and u2. And since there are no more variables with a negative reduced cost, the optimal solution of the primal LP has been reached. Now let's remind ourselves of the implications of the complementary slackness theorem and how we can use the optimal solution of the primal LP that we've just reached to obtain the optimal solution to the dual LP. So let's pull our values from the table. The 3 basic variables are u1, u2, and x1, and their corresponding values are on the right-hand side at 14, 18, and 6 respectively. The non-basic variables, x2, x3, x4, and u3, are all equal to 0. Now again, with the implications of the theorem. So taking the first slack variable of the primal, u1 is equal to 14. The theorem implies that since u1 does not equal 0, then y1, the first variable of the dual, is equal to 0. The second primal slack variable u2 is also not equal to 0, so the second variable of the dual, y2, is also equal to 0. Now the third primal slack variable is equal to 0, so the corresponding dual variable, y3, will not be equal to 0. So now we know 2/3 of the optimal solution to the dual LP. We know that both y1 and y2 are equal to 0. But we don't yet know the value of y3. We can use the rest of the information to find it out. So let's look at the primal variables. x2, x3, and x4 are equal to 0, which means that the slack variables of the second, third, and fourth constraints of the dual LP do not equal 0, which means that those constraints are not binding. x1, however, equals 6, which is not 0, so v1, the slack variable of the first constraint of the dual LP, is equal to 0. Now this is very helpful because it means that the first dual constraint is binding, and we can use this to determine the value of the as of yet unknown y3. So here is the dual LP. And the first constraint is circled in blue. We know three things about this constraint. We know y1 is equal to 0 and y2 is also 0. We know that it's a binding constraint, meaning that we can solve the equation as an equality since there is no unused resource or slack in the constraint. So substituting y1 and y2 in, we can see that y3 is equal to 8. So there we have the optimal solution to the dual LP. Easy as. Now it's always best practice to check that our solution holds up, and we can do so by substituting the optimal solution into all four constraints. Now remember that constraints 2, 3, and 4 were not binding, so there will be some slack in the equation. Looking at constraint 2, 4 times 8 is 32, which is greater than 30, so that checks out. Constraint 3, 3 times 8 is 24, which is greater than 20, and constraint 4, 2 times 8 is 16, which is greater than 10. So all the constraints hold, confirming our solution. Now, if you're feeling lazy and don't want to have to work out an unknown variable from a binding constraint, or you want to check your solution without having to sub in the solution to all the constraints, here is a little trick for you. The final table of the simplex algorithm shows you the optimal solution. The solution's given in the reduced cost values of the primal slack variables. What a neat trick. Now, as a final reminder, all that these colourful numbers and words are saying is that if you have a dual pair of LPs, you can find the optimal solution to one from the optimal solution to the other. Thank you kindly for watching.